So the notion that was introduced by Jerzy Neyman and Egon Pearson is the notion of statistical power, which helps us to predict and to protect ourselves from making the mistake of the second type, the false negative mistake. So what Egon Pearson and Jerzy Neyman did is basically they came up with this little table which lists 4 possible outcomes of a hypothesis test. In the columns of this table, you see 2 possibilities for the general population. That H0 is true. In terms of Cinderella, the number of white grains and brown grains in the box is really the same. And that H1 is true, that this number is different. So either H0 or H1 is true. But the bad news is that we cannot know which one is true. We have no access to the general population. We cannot count it physically. So we can only infer those assumptions based on our sample. And based on our sample, we make this inference by looking at the outcomes of a hypothesis test. So if the outcome is significant, we assume H1 and we say, yes, I'm sure that the effect exists. I'm sure that the proportion of grains is different. So of course, in reality, it may still not exist, this effect, and then we would be making a false positive mistake. But hopefully, in most cases, we would be correctly accepting H1, in case if H1 is really true in the general population. And there are 2 possibilities when we say, no, we cannot make any conclusion based on this sample. My outcome of my hypothesis test, my p-level is not significant, so my effect is too weak for me to be able to infer anything about the general population. And again, we may be right. If there is no effect in the general population, we cannot detect it in our sample, but we cannot say anything about the general population, so probably we're not going to go to the ball in this situation. And there is a false negative mistake. When we say there is no effect, or rather, we cannot conclude anything about the general population, and even if there is an effect in the general population, we cannot conclude anything about it. So in these 3 situations, we'll miss the ball, and only in this situation of correct acceptance will Cinderella be able to go to the ball. That's why evaluating the chances of this correct acceptance is crucially important for her, and it's crucially important for us as researchers. That's why there are 2 probabilities rather than 1 that we need to bear in mind when we perform statistical hypothesis tests. One probability is called our p-level, or our level of significance, and this is basically the chance of making a false positive mistake. If I choose H1, my p-level tells me whether the probability of making a mistake, assuming that H0 could be true. But there is also another probability, which is called statistical power, which quantifies the chances of not making a type 2 error. So the probability of type 2 error is labeled as beta, and the probability of not making a type 2 error, that is of discovering an effect in case if it's really out there, this is our statistical power. So just to recap a little bit, significance level are the chances that we get this effect in our sample if it does not exist in the population. And statistical power are the chances that we get this effect in our sample in case if it does exist in the population. So this is the chance of discovering an effect that exists. Now, because we don't know whether an effect exists or not in the general population, the best we can do is to calculate those 2 probabilities to make sure that we are well protected against both possible mistakes. And this is what we do in practice. So in research, we calculate our statistical power to decide on how large a sample do we need to have in order to be able to discover the effect that we are looking for. And in case if our power is really high, then even if we don't discover any effect, we can potentially make some substantive conclusions. For example, if my power to detect an effect was 0.95, which means that there is only 5% probability that I could have missed it, then I can conclude that probably an effect of this size does not exist in the general population. Maybe it exists, but it's weaker, but not the one that I was looking for. But if your power is low, if your chances of detecting an effect initially were not so high, then failing to discover anything, basically your study does not provide any much useful information. It's basically not a very well designed study. That's why it's best to aim for high-powered studies. Now, what does our statistical power depend on? The fairy godmother can tell us that it depends on three things: sample size, effect size, and your desired significance level at which you would like to reject your H0 and accept your H1. How does power depend on those things? Well, obviously, the larger is your sample size, the higher is your chance of discovering an effect in your sample, if it exists in the general population. The same for effect size. The stronger is your effect, the higher is your chance of discovering it. But with desired significance level, it's a bit more tricky. If you are using a more strict significance level, you reduce your statistical power. Sometimes it's not very strong, this reduction. Sometimes it can be crucial. And also, your statistical power depends on what statistical procedure you are using. This is not possible to quantify without a complicated simulation. But the general idea is that if you're using a statistical procedure whose assumptions correspond to the properties of your data, statistical power is higher. So for example, if your distribution is normal and your scale is interval, then Pearson correlation will have a higher chance of detecting an effect than Spearman correlation. But if your distribution is non-normal, it's skewed, for example, and your scale is not really interval, then Spearman correlation will have a higher chance of detecting the effect that you're looking for. So that's why choice of statistical test is important, and we'll discuss those issues in detail in our 8th unit. So just for an illustration, I asked the fairy godmother to simulate for us Cinderella's situation. And of course, statistical power depends on three things. We are not able to plot them all on one graph. So each time we'll explore how statistical power depends on one thing, holding two other things constant. In this situation, we are looking how power depends on sample size, holding effect size 0.06 constant, and our desired significance level also constant, p less than 0.05. And you can see that this dependence is dramatic. If Cinderella is only willing to count 100 grains, her chances of discovering a significant effect are just slightly above 50%. So in about 1/2 of the situations, she's going to discover this effect if it exists. And in the other half of the situations, she will not be able to make any conclusions. But if she were willing to count 200 grains or even more, her statistical power would have been much higher. And with a sample size of 300, she would be completely sure not to miss this effect. Her power would be about 0.95. So the larger your sample, the higher is your power. The second thing is a bit more tricky. Here you can see how statistical power depends on effect size, holding sample size constant. So we always still draw 100 grains. What is our chance of discovering a significant difference in our sample? Depending on how unequal is really the proportion that the stepmother has put in the box. Now, because here we are playing the role of the cruel stepmother, when I simulated this data, I put in the box 60% of white grains. And for this proportion, the chances of discovering a significant effect are about 50%, as we've just seen before. But if the proportion of white grains was 2/3, then statistical power would have been above 0.90. And vice versa, if the proportion of white grains was 55% to 45% brown, the power would have only been 0.20, very low. So you see that this association is nonlinear, and intuitively it's very hard to kind of predict it without making the simulation. And finally, here you can see holding effect size and sample size constant. You can see how power depends on desired significance level. So if Cinderella is using a p less than 0.05 significance level, her power is slightly above 0.50. If she wants to use a stronger significance level, for example, p less than 0.01, her power would drop to 0.30. And if she used p less than 0.001, as we use in medicine, her power would have only been 0.10. So her chances of discovering the difference, the effect that is really out there, would have been very small. And vice versa, if she went up and relaxed her significance level to 0.10, this would have increased her statistical power a little bit. In this particular case, this difference is very small, but in some situations, this difference can be drastic if you have a very small sample, for example. So sometimes, if you want to reduce, if you want to relax your significance level, statistical power is the argument that you need to use to justify this to your reviewers or to your thesis advisors. But you're only allowed to do it in very small samples when there is no way physically that you can get more data. And you need to be aware that the price you're paying is you cannot be so confident that the effects you see are not false positives. Unfortunately, everything has a price in science. So how do we go about if we want to calculate our statistical power? Imagine that you're looking for some effect, for example, a correlation of 0.30. How many people you would need to recruit in your sample in order to be confident that you're going to see this correlation in your sample in case it exists in the general population? There are different tools that we can use. Unfortunately, in SPSS, power analysis only comes as a paid add-on, and it's only in some analysis that SPSS gives observed power, which is anyway is not very useful. The good news is that there is special free software, GPower. Unlike R, which obviously can also do the job, GPower does not require you to perform any programming. It's a completely graphic interface point-and-click type of software. And it's completely free, available from the University of Hanover. So if you follow this link, you can download it and install it on your computer. And in GPower, you can ask 3 types of questions. The power analysis, which is called a priori, when you determine your sample size based on your expected effect size and based on your desired statistical power. So the question is, how large a sample do I need to achieve this power for this effect size? Another type of analysis, which is also quite helpful, is called post hoc. If you want to evaluate the power of someone else's study or your own, or you want to evaluate the chances of replicating this finding, assuming everything holds equal, same sample size, same effect size. Your power for a post hoc power calculation will give you the power for a repeated test of the same effect in the same sample. And the third type of analysis is called sensitivity analysis. Again, if you know sample size, you can ask the question, what is the minimum effect size that I will be able to detect with sufficiently high power? What is the weakest effect that I can discover given such a sample? Now, just to show you an example of G-power, basically if you run this software, your window looks pretty much like this. And here in this window, you first of all, you choose what kind of test that you want to calculate your power for. In exact tests, you calculate it for correlations or for proportions, like the binomial test, which we just did. In the f-tests, you can calculate power for ANOVAs, MANOVAs, and other linear models. Unfortunately, it's slightly more complicated because the effect size measure that G-power expects is not quite the same as the one SPSS produces, but Dan Lakens has written a nice paper on that, a nice tutorial. T-tests, obviously comparing the means. Power for chi-square tests, and as well as power for some z-tests when you use normal distribution to judge the significance of difference between two correlations, for example, or two proportions. This is all based on z-tests. So we are just interested in correlations. So let's go to exact. And here we choose correlation bivariate normal model. That's our good old Pearson correlation. And a priori, let's compute required sample size to start with. What are the input parameters that we need to enter? So first, it's the number of tails. Is our hypothesis one-tailed or two-tailed? I'm not sure why by default it gives one tail. In principle, it would be more correct to set two tails straight away. Here, correlation for H1 is your expected effect size, for example, 0.3. Your desired significance level, alpha, your desired power, well, let's say 0.80, and correlation for H0. This is basically the value of correlation under null hypothesis, and almost always it's 0. I don't think we ever need to change it. And you simply press calculate. And first of all, you get this total sample size, which is estimated at 84 individuals. And your actual achieved power is 0.80, just as we requested. And here there is this nice little graph, which is very useful to understand where all these figures come from. On this graph, you can see two different distributions. If you ever forget what these distributions mean, you can always come back to this slide, or you can simply look at their midpoints, at their means. For the red distribution, the mean is 0. And this 0 is the distribution of findings in independent samples under null hypothesis. So if your correlation is really 0 in the population, these are the results that you will see with various probabilities. Sometimes you can see correlations around 0, but sometimes it can be minus 0.2 or minus 0.3, and sometimes 0.2 and 0.3. And two tails of this red distribution are cut off with these little green lines, which correspond to critical values of correlation coefficients, the minimum values of correlations that will be significant at this sample size and at this significance level. And here there are two tails together, they correspond to 5%, 1 minus this alpha of area under this curve. Now, the blue distribution is a bit more interesting because it's a distribution of results that you will see, assuming that the true correlation in the general population is 0.3. In most cases, your correlations will be around 0.3, 0.4, 0.5, but sometimes they can go as low as 0.2 and 0.1. And sometimes these correlations will be weaker than the minimum critical value. So this portion of this area to the left of this green line, which is marked with the Greek letter beta, denotes the probability of making a false negative mistake, of missing the effect that is really out there. And the rest of this blue distribution area, 1 minus beta, corresponds, basically it's your statistical power. Now, yes, because the true value of correlation that we set here is 0.3, maybe it would make sense to test also this using a one-tailed hypothesis, because we kind of know. So for post hoc, situation is pretty much the same. Imagine that we set our sample size to a certain value that we've had in the past, and we can calculate the power, which can be pretty good for a large correlation. But of course, if it's a smaller correlation, then obviously our power will drop. And here we can see the protocol of power analysis that we can copy, and an XY plot for a range of values that we can draw, which is basically the similar kind of plot that I showed you before. So G-Power is the software to use when you're planning your research, when you're trying to set up your analysis. So even for correlation by default, it makes sense to use two tails if you don't know in which direction it might go. But if you know which correlation it should be, then you can sometimes test a one-tailed hypothesis. So it depends on your research situation, actually. But I hope the general idea of G-Power is clear, and I hope that you can explore it later on in your seminars. Now, the tricky substantial question is, how do I decide on my target effect size? Because in order to set my target effect size, I need to know it. Where do I get this information? Well, if someone has already tested the hypothesis that you are trying to test, for example, you are replicating, then it's very easy. You just borrow this effect size estimate from a past similar study or from a meta-analysis, which has summarized several studies if it exists. Unfortunately, a much more common situation is that no one has investigated this effect before. Then you have two options. Either you can look for sizes of similar effects in your research area and kind of or an average effect in your research area. There are also meta-analyses that try to come up with those findings. Or you can say, I will just take a minimum effect size of practical significance. For example, you are developing a questionnaire to recruit people during employment, to assess people during employment procedures, and you're looking to investigate the correlation between your questionnaire scores and the future work performance. Obviously, collecting this data costs a lot of effort, if not money. That's why you can say, okay, if the correlation is 0.2 or above, I'm interested in it. But if a correlation is less than 0.2, maybe this test is not going to be very useful anyway, so I'm not going to be very interested in that correlation. And you say, okay, my minimum effect size of applied importance is a correlation of 0.20. And you can set up a sample size so that you will be sure not to miss this correlation of 0.20. And what is your target power supposed to be? That's fairly easy. If your study is not very large scale and not very costly, and especially if you have several experiments, then a minimum level of power of 0.80 is probably sufficient. Even if you fail to discover an effect in one experiment, you will discover it in another one, and altogether it will be fine. But if your study is very costly, if it's large scale, then I would probably aim for a power of 0.95 to be more confident. Because if I spend $1 million conducting a study, obviously even 20% of this 20% chance of this $1 million going to waste is not so acceptable. So I hope you have a general idea of how power works. The final little issue that we need to discuss here is, what do we do with non-significant results? And this is again where the paradigm has changed. At the beginning, researchers with no heads who cared only about significance levels would basically throw away non-significant results because they would think, okay, a non-significant result does not let me conclude anything in favor of H1 or H0, so it's not worthy of being published, it gives me no information. But this approach is completely wrong. Under the new statistical paradigm, when we focus on effect sizes and we can calculate confidence intervals, even if the effect is non-significant, and then our confidence interval would include the point which corresponds to absence of effect, to H0, but still we get some information about the distribution of this effect. We get an information about an estimate of this effect in this sample. Even if we cannot conclude that this effect is not due to chance, still this information can be useful. It can be combined with data from other studies to improve the quality of our overall estimate. And let's, just as an example, let's try to apply this notion of confidence intervals to Cinderella's findings. So for a binomial test, it's very easy actually to calculate a confidence interval. The formula is here, provided by the fairy godmother. And here is the proportion of white grains obtained in each of the 5 Cinderella's trials. The point which corresponds to H0 is equal proportion of white and brown grains, that is 0.50. And for each of those values obtained in independent studies, I have calculated the boundaries of this confidence interval. So basically, based on this study, we can expect that the true effect size of the general population is supposed to lie within these boundaries with 95% probabilities, assuming that this effect size kind of hits the center of this distribution. And as you can see, these 3 are significant, and here the confidence interval does not include the point which corresponds to absence of effect, 0.50. This, we can call it 0.0, but it's not always exactly 0. So for binomial test, it will be probably in most cases 0.50 or some other value that corresponds to H0 in your case. For a correlation, it will be 0. And for many other statistics, it's also going to be 0. And here you can see that there are 2 trials where the result was not significant. And here, the left bound of this confidence interval is below 0.50. So confidence interval includes 0.50. And it's a 95% confidence interval, so it corresponds to p less than 0.05 probability. But even if we use a stronger cutoff for significance level, we still usually provide always 95% confidence interval. I don't know why, because probably it's just a traditional. But then again, what happens if we can combine the effect over 5 trials? And this is the case that you often observe in science. 5 independent studies, the results are seemingly inconclusive, but if you are observant, if you are smart and reflexive like Cinderella, you may have noticed that all of those effects go in the same direction. The proportion of white grains is always above 0.50. It never happens that the proportion of brown grains is larger. So even if this effect is sometimes in some samples is very weak, still it's kind of consistent. So if we combine all these effects over 5 trials, we just add up the results and we get 305 white grains out of 500 in total, or 61 out of 100 on average. And the confidence interval is going to be much smaller now. The boundaries are more narrow, and the significance level that corresponds to the p level that corresponds to these 5 trials combined is much stronger now. It's 1 chance in 3.2 million to get such or more unequal proportion. However, even these 2 trials taken alone are quite useful. So here, Cinderella was lucky to get a significant result at the beginning, Why? Because we set the random number generator to a magic number 333. Now, if you try setting this random number generator to a different value, for example 2020 or something like this, you might actually easily get 2 or 3 results at the beginning that are not significant. So if you don't know that you have low power, you might say, oh, my result is not significant, maybe this hypothesis doesn't work, I will give up this study. But throwing out non-significant results is a very bad strategy. Because imagine that these 3 studies that were successful don't exist. Imagine that only 2 non-significant results exist. But if we try to combine them together, they provide this estimate of our effect, 0.575 white grains on average. But as you can see, the confidence interval does not include 0.50 now. Thanks to a larger sample size combined, now we can be confident that this effect is not due to chance, even if it's not strong. So this is the reason why non-significant findings should not be thrown away into the garbage bin. And another reason, which is maybe even more important, is that in order to correctly estimate the size of this effect in the general population, we actually need to have all of this study, including non-significant ones. If we only publish these 3 and don't publish these 2, we can calculate an average effect size based on 3 significant results, but it will be biased up. The estimate that we will get will be 0.63 or 0.64, something like this, because we will only see 1/2 of the reality, the situations when the effect was slightly above its true value in the general population. So our estimate will be biased. That's why if we want to arrive at a precise, unbiased estimate of population effect size, we need to put together all the studies with significant and with not significant findings. Unfortunately, people still don't often publish non-significant findings. And that's a problem. Now, of course, journals are increasingly realizing that it's very important to publish all results, regardless of their statistical significance. Maybe the only criterion to decide whether this study is worthy in principle of being published is statistical power. If it's low, the study is not so relevant. Maybe it's low because there is no way to get physically more data, then it's okay. But if a person could have gotten more data, but they just were too lazy to do it, and the power is low, then probably reviewers are going to reject this paper at the very beginning. But if the study is well designed, if it is focused on a relevant research question, and if it possesses sufficient power, then in many journals there is now this option of pre-review. You submit your research proposal to this journal and they approve your research design, and then they commit to publishing your results regardless of the exact estimate of your effect. Even if it's non-significant, they are going to publish it because they have already accepted that your study is testing a valid hypothesis. Why? Exactly to prevent this situation of non-significant results being filtered out just because of their effect size. So we explored a little bit this issue of statistical power, and I hope that you have some understanding of what power is, why it's important, and what are effect sizes, and what are their confidence intervals. So in the next section, we'll focus in more detail on effect sizes, this very key concept of our psychological research.